Hello and welcome. This is the second video in chapter 25, and in this video we introduce the topic of electric potential. First things first, we have the definition of potential. The units, it's defined as the electric potential energy between the source and the test charge divided by the magnitude of the test charge. And so those units are joules per coulomb. We define that as a volt. Yes, electric potential is going to be the thing that has units of volts, and it will be the thing from which we get our voltage. So that's important. What is it though? Okay, the electric potential is kind of similar to the electric field in that it is created by a source charge. It's created by a source charge, and when a test charge is in that potential, okay, when I say that it's created by a source charge, it means the source charge alters the space around it such that when a test charge is in that space, it feels the effect of the potential by acquiring an electric potential energy. Unfortunately, the names potential and electric potential energy are similar, and so we have to contend with the fact that they inherit kind of some natural confusion. So that's something to look out for about the differences between potential energy and electric potential, right? So that's the big difference, though, is that electric potential is a scalar quantity, and that's great because you don't have to find components in all three directions to find the potential of a charge distribution. You only have to calculate the number, and you usually only have to deal with the distances. So what we'll do for these next few slides is go through different basic charge distributions and try and visualize, talk about the formulas, and also try and visualize what that electric potential looks like. Okay. One quick reminder, though, is that the potential in a region of space will increase or decrease. And that means that a positive charge, so a positive charge will speed up in the direction of a decreasing potential. So a positive charge is kind of like a marble rolling down a hill, right? The marble by itself is going to naturally roll down the hill, from higher to lower elevation. This is like a potential speeding up as it goes from higher to lower potential. But the negative charge is the opposite. You don't see this effect in gravity. You don't see a marble spontaneously rolling up a hill, increasing speed. But that's exactly what happens to the negative charge. The negative charge speeds up in an increasing potential because it has a minus charge. And so it slows down. This would be like this would be like shoving, a marble or a box down a hill if it's a negative charge and have it magically slow to a stop, well, without friction. Yeah, it wasn't a great analogy. So a quick review from chapter 23. This is the formula for the electric field of a parallel plate capacitor. Okay, it depends on the charge of the plates and the area of the plates, and the electric field is a vector between positive and negative, always pointing from positive to negative. This is your analogy of infinite flat Earth, right? At every location in space in between those positive and negative charges, the electric field is constant. Every point has a vector that points towards the negative, away from the positive with the exact same value. So just imagine filling in that space in between the positive and negative charges with vectors, all of which point towards a negative and are constant. So that's the review. Now, what about the new stuff? What about the electric potential in between these plates? The electric potential in between those plates, which it looks like we're kind of stating without proof, which is fine. The electric potential is an increasing function from negative to positive. So the electric potential starts off at a value on the negative plate, and it increases to a final positive maximum value on the positive plate. So this is like in contrast to the electric field. The electric field is constant throughout the space in between the plates. The electric potential is increasing from positive to negative. and it's also a scalar. So it's not, we're just looking at a numerical value. This is like temperature, right? The temperature in a room, it might be a three-dimensional function, or it might be a function that assigns a number at every point in three-dimensional space, but that number is still a number, right? It's still the temperature, right? In a macroscopic sense. Potential is like temperature in that regard, where it's only a numerical value at a location in space, which might be 2 or 3 dimensional. So, sorry, quickly going back to this slide, that's the formula. So the formula for the potential between positive and negative is E times S, where again, we set the S to be 0 at the negative and increasing in positive towards the positive. But here's the important thing about potential, is that if we define the difference, we can define the voltage. We define the voltage between 2 points as the potential, the difference in electric potential between those 2 points. For instance, what's the voltage across, we sometimes say across, what's the voltage between the 2 plates? Well, it's the value of the potential at the, it's the value of the potential at the positive plate minus the value of the potential at the negative plate. So just be strength of the field, electric field E, times the distance between the plates, which is usually specified by D. And so this in turn gives us a new way to find the units of the electric field. Okay, in those previous slides, you had potential equals field times distance. Okay, we know that field is newtons per coulomb, but you can show, it's pretty easy to show, you can show that the electric field is also volts per meter. And when you look at most electronic devices, if there's a field that needs to be, electric field that needs to be measured, it'll typically be volts per meter. So we're going to stick to volts per meter instead of the standard newtons, SI newtons per coulomb. Newtons per coulomb is only there to kind of set up the basics of the field, but we're usually doing volts. And the importance of voltage and the importance of electric potential is that it's easier to measure. It's a lot easier to measure and it's a lot easier to calculate than electric field, but that's how they're related. So this is a couple ways to visualize the electric potential. Again, what are we trying to visualize? We're trying to visualize, in this case, of a parallel plate capacitor, we're trying to visualize a number at every location in space in between those plates. So there's a couple ways that we can do that. The first one is just a graph, right? That's the one that we've already seen. It's a graph, since it's kind of has symmetry here, we can express it as a graph. But these, on the picture on the right, these are called equipotential surfaces. These planes, these geometric planes in between the plates. And these equipotential surfaces represent two-dimensional surfaces where the value of the electric potential is constant. Okay, that's what an equipotential surface is. It's different from a Gaussian surface from Gauss's law. It's just the value of the potential being constant. The third picture is like a cross-section of the second picture, where you just look, this is like a side-on view of the second picture, which, to be honest, this picture on the left here is probably one of the most common types that you'll see out there in simulations, like the simulations that we're doing in class that have these depth simulations. The final one is an elevation graph, and this elevation graph gives you kind of the picture of what a positive charge would do. So a positive charge is going to go towards the negative, just like a marble is going to roll down the hill. What you have to be aware of, though, is that a negative charge is going to speed up the hill, whereas a positive charge speeds down the hill. So that's the first basic type of potential, the first basic formula for potential based on a specific charge distribution. Okay. Let's see. One thing that we can immediately notice, and it'll turn out to be true in general, is that we have the equipotential surfaces pointing parallel to the plates, and the electric field is pointing perpendicular to those surfaces. So the electric field points perpendicular to the equipotential surfaces of the potential, and it points towards decreasing potential, as we see in these pictures here. So here we've got three different instances of setting the zero of the electric potential. You can set the zero of the electric potential wherever you like, because it's not physical, just like position is in Physics 1, right? On day 1 of physics, you learn about the position, right? And if you think about a ball on the floor in a room, right, what's the position of that ball? It depends on the origin and the coordinate systems that you use. Same thing here. The value of the potential depends on the zero that you choose. So different zeros will give you different values of potentials, but what stays the same or across all three of these pictures is the difference in this potential between point to point. So for instance, let's take the first and the third, not the first and the third, but these two contours on the left and the right here. So on the right-hand graph, the left contour is at 75 volts and the right contour is at 25 volts. What's the potential difference? What's the voltage between those contours? Well, it's 75 minus 25, it's 50 volts. And you'll see that the potential difference between the two contours in the middle, so in the middle graph, the voltage between the two left and right contours is still 50 volts, and it's still 50 volts. So going back to position, if a ball on the floor moves from point A to point B, no matter what the origin and coordinate system, every person measuring it agrees on the displacement. Same thing here. No matter what the zero is, every person agrees on the value of the voltage between 2 points. That is the difference in the electric potential. So that concludes this next video in chapter 25. In the following video, we'll talk about the electric potential of a point charge. This is an important one, and we'll start to make some connections between this and the electric field. Until then, thanks for your time. We'll see you back here for a third video. Take care.